Let me welcome you to this lecture 5 of our course on reinforcement learning. And today's lecture marks the end of the 4 lecture series on foundational issues on the subject, and the beginning of the next phase of the course, which is more focused to particular methods and applications. It's a selective focus, and it will go deeper than what we have gone into in the past. And so today we're going to start with a review of finite horizon problems, the relation to infinite horizon problems. Then we're going to focus on rollout, discuss rollout in general, then focus on rollout for deterministic finite state problems. In subsequent lectures, perhaps a couple of lectures from now, we're going to return to stochastic problems, but today we're going to focus on finite state deterministic problems. An important property of rollout, the cost improvement property, which says that the rollout policy performs better than the base policy, the base heuristic that you started with. Then we're going to talk about variations of deterministic rollout, extensions, and so on. And we're going to have animations, demos today for you. 2 or 3 animations related to rollout, where we're going to illustrate these properties. So review of finite horizon problems. I'm going to go through this relatively quickly. We have a discrete time dynamic system with state xk, control uk, wk random disturbance. It goes over n stages, and at each transition, it generates a random cost. The cost function is the sum of the stage costs plus a terminal cost at the terminal state. And because this is random, because of the presence of wk, we take expected value of that. And we consider policies, which are sequences of functions, mu0 up to mu n minus 1. And we also call them feedback policies or closed loop control laws and so on. Each of these mu's is a function of xk, of the current state. And mu k can be viewed as a lookup table that tells us that if you are at a particular state xk, you apply uk. That's what we aim to have this lookup table and go forward from x0. And for each state that we encounter, look up the control from the lookup table. And given a policy, there is a corresponding cost associated with the policy. We plug in the control dictated by this policy, take the expected value, and this is the cost of the policy pi at starting with initial state x0. And the optimal cost function minimizes overall policies and gives you a function of x0, j star. And an optimal policy is the one that attains the minimum. And this is given by dynamic programming. Now, in our review, we're going, and also in this lecture, we're going to be focusing primarily on finite horizon problems because they are most convenient for the rollout algorithm. The rollout algorithm makes more sense to start to develop it for finite horizon problems. On the other hand, everything applies to infinite horizon problems with minor adaptations. So let's review the dynamic programming algorithm. It gives you the optimal cost functions of the tail subproblems that start at the different stages. We start from the terminal cost and go backwards. From j star k plus 1, we get j star k, xk, with this formula here. And it involves a minimization of your uk, which also provides the optimal policy. At the last step, after n stages, it gives you the optimal cost function of the n stage problem. And the optimal policy is to use the minimizing uk at each state xk that you may be. Now, this algorithm is very formidable. It's hopeless to apply it except for trivial academic problems or specially structured problems like the linear quadratic problem, about which we talk about quite a bit. The objective of reinforcement learning is to solve approximately problems like that in their infinite horizon versions. And a principal method of reinforcement learning is approximation in value space. And the idea is very simple. There are these J stars that are hard to calculate, so we replace them with something else, some approximation that can be obtained more conveniently. And after we have these J tildes, we can go forward, generate controls at every state that we might be, xk. We do this minimization with J tilde taking the place of J star. So this is the online play, and offline training may be the calculation of this J tilde, perhaps. And there's also a multi-step version of approximation in value space that we have talked about. And we also noted that there are many different ways to calculate these J tilde functions. Online rollout, offline training with a neural network or something similar, problem approximation, using the optimal cost of a simpler problem as your J tilde for the more complicated problem, use various heuristic cost functions, and so on. And let's also discuss infinite horizon problems, review them quickly. Here we have the same structure as for finite horizon problems, except we have infinite number of stages and a stationary system and cost. In other words, this F and G does not depend on K. And there's also a discount factor alpha to the K, which may be 1 or maybe less than 1. The cost of a policy is, the policy pi is the limit as n goes to infinity, as the horizon goes to infinity of the finite horizon costs. And the optimal cost function is obtained by minimizing overall policies. And there's Bellman's equation. Bellman's equation is the limit of the dynamic programming algorithm as the finite horizon optimal cost converge to the optimal infinite horizon cost. And there are a couple of important problems that fit this category. One is discounted Markov decision problems, where you have finite state and action spaces, and alpha is less than 1. These are the good guys of reinforcement learning, the ones that most of the artificial intelligence literature deals with these discounted problems. Now, these are not the only ones. There are other important problems that in particular, stochastic shortest path problems, where you have a goal state that you're trying to reach. And this goal state is cost-free and absorbing. Okay, so once you get there, you stay there. Like games, for example, like chess, have a goal state or a termination state, namely the end of the game. And for these, alpha is equal to 1, and under some conditions, these have as good an analytical and algorithmic theory as these. And these are very important also in practice, like these are. These are the two principal models. There are some other ones that we are not going to be going into in this course. So this is the analytical theory, centers around Bellman's equation. And there's a computational theory. There are two computational algorithms. Value iteration, which generates the finite horizon optimal cost functions. JK, starting from some J0, it uses this recursion. It's a dynamic programming recursion, right? And it can be interpreted as such. And this is value iteration, it has good convergence properties. And the other algorithm is policy iteration, which instead of generating sequence of cost functions, generates sequence of policies, mu k, and their cost functions. The initial policy is arbitrary, and the typical iteration of the typical iteration here consists of two steps. Given a policy, mu, it generates a new pure policy, mu tilde, in two steps. Policy evaluation, which computes J mu, the cost function of mu, and then policy improvement, which computes the improved, the cost function of the improved policy mu tilde, using the one-step look-ahead minimization, where in place of J tilde, we use the cost of the policy we started with. Mu is generally called the base policy, okay? It will resonate with the terminology that we're using in rollout. Mu tilde is called the rollout policy. And indeed, we have noted that rollout is a single policy iteration, starting from the base policy. And if you were to do continuous rollout, a perpetual rollout, you would get the policy iteration algorithm. And in principle, this has, if you execute it exactly, it converges to an optimal policy. On the other hand, with approximations, when you use approximate policy evaluation, it will not. And later, we are going to discuss a little bit more its behavior. But these are the two main algorithmic procedures. And there's an important conceptual idea that I'd like to bring up. Finite horizon problems and infinite horizon problems are very much connected. In particular, an important fact is finite horizon problems can be transformed to infinite horizon problems. So if you have a method that looks more convenient for infinite horizon problems, it can also be used for finite horizon problems using a certain transformation that I have in this figure. Okay, so we have a finite horizon problem. How do we transform it to an infinite horizon problem? Well, the finite horizon problems has state spaces, x0 for stage 0, x1, x2, up to xn. These are the state spaces, and we form an infinite horizon problem whose state space is the union of all those plus a termination state at the end of the horizon where we go there and stop there. We don't generate states anymore. Okay, so let's look at the structure here. These are the states of the first stage, and again, the states of the second stage, and so on. Starting from an initial state in the space x0, then we set up the problems where we make transition to the space x1, then to x2, all the way to xn, and then when we are at xn, we transition to the termination state, and that's that. Now, the costs of these transitions are exactly the same as the costs for the original finite horizon problem. Let's start from here, from states in x1. Then we go from x1 to x2 and so on, and end up after n-1 steps, we end up to the termination state. So if you focus attention on these transitions that start at x1, what do you have? And what's the optimal cost of this transition process? Well, it's the tail subproblem. This problem here is the tail subproblem that starts at x1. And this problem here, the sequence of transitions and cost generations that start from here, are the corresponding transitions of the tail subproblem that starts at stage x2. So if you calculate the optimal cost function of the infinite horizon problem at j star for each one of these states, what you will get is the tail subproblem cost functions from j0 star to j1 star, j2 star, and so on, all the way to the end. And of course, this terminal cost function is just the terminal cost of the problem, jn star. And if you look at the Bellman equation of this infinite horizon problem, it is exactly the same as the dynamic programming algorithm for a finite horizon problem. Write it down, take into account the special structure of these transitions, you'll see that they are exactly the same. So when we say that approximation in value space is a step of Newton's method for the infinite horizon problem, if we transform a finite horizon problem to an infinite horizon problem, then we get a corresponding Newton step statement about approximation in value space in finite horizon problems. conceptually they're the same. So this is very helpful to transform in your mind methodologies and results and concepts from one context to the other. We generally discuss Newton's method for infinite horizon problems, but everything applies to finite horizon problems, and the insights that we get about approximation in value space being one step of Newton's method, similar approximation for multi-step, for the case of multi-step look ahead, all of this applies to finite horizon problems as well. So all of this is going to be in the background. We're not going to be dealing very much with it, but it can all be taken back to this basic conceptual framework, whether it's finite horizon or infinite horizon. So the policy iteration Newton step ideas apply to finite horizon problems. That's the bottom line here. And one of the benefits of thinking abstractly and transitioning between finite horizon and infinite horizon. Okay, any questions? Okay, so now let's talk about rollout. It's going to occupy us for 2 or 3 lectures. Generally, rollout can be viewed as a special case of approximation in value space. You have seen this equation before. At a given state, we minimize the sum of the cost of the first L steps plus the cost of the future as approximated by some J tilde. Now, in the case of rollout, J tilde is the cost function of some base policy. And here I'm showing multi-step look ahead. Of course, we're familiar with one-step look ahead, which is we have related to Newton's method. And at a given state, we do this minimization, we obtain a sequence, and the first component in that sequence is the rollout control U tilde K, which defines the rollout policy mu tilde K. So we use the terminology that the policy used for rollout is the base policy, and the policy obtained by look-ahead minimization is the rollout policy. And here there are approximation variants, other methods of approximation value space that are inspired or partially involved a heuristic. And other approximations, for example, in this formula here, we talked about using certainty equivalence for all the steps after the first one to simplify the calculation of this expected value. Other possibilities include truncated rollout, which involves approximations of this J tilde function by using a number of steps of the base policy. A lot of approximation in value space revolves around rollout, either explicitly or implicitly. There's always some idea of looking into the future, and if you have some good heuristic, it may provide you with a good means of looking into the future. That's the general idea, and it manifests itself in different approaches for specific problems, also taking into account the structure of these problems. So rollout is going to be central for our course, and it's also a very important concept in approximation value space. And the reasons are that it provides important options for cost function approximation in the context of value space methods. And if you look at these figures around Newton's method, you'll see that, that generally approximations of J star from above, larger approximations, are better than approximations from below. And rollout always gives you something from above, right? Because this is the cost of some suboptimal policy, and this is the optimal cost. So this is also part of the secret for the success of rollout. It not only it's an approximation to use, a J tilde to use, but it also approximates from some good region, from above. The other important role of rollout, it's the building block for the fundamental policy iteration algorithm and its approximations. For example, we'll see things like double rollout, 2 iterations of rollout, or multi-step rollout, and or policy iteration involving neural network approximations. Rollout is right in there. It's a fundamental building block. So what are the reasons for its importance? For one thing, in its pure form, among all the reinforcement learning methods that you'll hear about, this is the easiest to understand and the easiest to implement. It's very easy to implement rollout on your own. You don't need any off-the-shelf software, neural network packages, machine learning packages, which you don't know what's in them. And you can write your own code and understand every bit of it. Then I mentioned earlier in the course that all the reinforcement learning methods are flaky, okay? Take this as an axiom. Nothing is guaranteed in reinforcement learning. You try a method, it may or may not work for your problem. And you may have to tune it also manually so that it works on your problem. But of course, it may not work for a different problem with your own manual tuning. Now, in this landscape of unreliable methods, rollout is by far the most reliable. It works almost always. Easy to implement, easy to test, easy to works almost always. It's relatively easy to tell when it succeeds because you have this base heuristic and you expect rollout to do better, much better than the base heuristic. If you don't see that, then something's wrong, okay? This is a reliable guideline. Now, if you take some of these other methods, DQN, policy gradient methods, for which there's a lot of literature and a lot of successes for individual problems and a lot of failures that people don't talk to you about it, these methods are by far more flaky than rollout. And then, like I said, they require manual tuning, which may require anything from a few hours, a few days, or infinity. In other words, the manual tuning may never work. And then you have to switch to another method. And you don't know what went wrong. Also, the other problem is that you get these methods to give you correct numbers. Your program doesn't crash. It gives you numbers. On the other hand, it's impossible to tell whether these numbers make sense. It's very difficult to tell whether these numbers make sense. Is it a good solution? It's always a suboptimal solution. But is it a good suboptimal solution or a bad one? And how can you tell? Rollout has this problem to a far lesser degree. Okay, so this is as a warning for you as you navigate this landscape of I would say, the jungle of reinforcement learning methods and try to survive. Another thing about rollout is that it's very general. It applies to deterministic problems, to stochastic problems, finite horizon problems, infinite horizon problems, with a mathematical model or with a computer model instead of a mathematical model. Instead of equations, have a computer model, a simulator. There's always a model, okay? Don't always remember that. There's always a model which is perhaps hidden inside a computer. And rollout will work both with equations as well as with a computer model. But of course, like all methods, if you don't have a mathematical model, you're in for a lot more adventure, okay? Its problem becomes harder, primarily because very often you don't know what's inside the simulator, but also for other reasons, because there's a finite simulation budget. You want to compute an expectation, but simulation will give you only an approximation to the expectation. There are all sorts of bad things that can happen when you're using computer models or simulators, as opposed to having clean equations and well understood rules of transitions. Okay, rollout relates to Newton's method. That's the hidden sauce inside that underlies its success. Other methods do not have this property. It can deal well with online replanning in the sense that if there are some parameters in your system that change over time, then as long as you know what these changes are, it's a very simple adaptation to implement these changes into the rollout algorithm. So it provides a useful alternative to reoptimization in adaptive control. It is connected to model predictive control. It's an integral part of the basic model of model predictive control. And also it relates to issues of stability in model predictive control settings. Finally, it can be combined with many of the other reinforcement learning methods that are used in practice, including methods of Q-learning, aggregation, approximate policy iteration using neural networks. These methods can give you policies that you can use as base heuristic, okay? So there's a natural way to combine rollout with other reinforcement learning methods. Use this first for approximation for offline training to get a base policy that you can use online in the context of rollout. Okay, so let's go to rollout for deterministic finite state problems. First of all, let me remind you what we mean by a deterministic optimal control problem. It's a problem like the one I gave earlier, except that there is no WK. Have n stages. This is a system equation, xk the state, uk the control. The cost function is like that. There's no need for expectation. And what we need to do is minimize overall control sequences. This expression, the optimal cost function is J star, given by this formula. Now, finite state deterministic problems. A finite number of states, a finite number of controls have a nice representation in terms of a graph and a shortest path problem. So here's the figure. Here are the various stages. Stage 0, state 1, the states x0 are over here, x1 are over here. The state space does not need to be the same for every stage, right? If there are n of them, we introduce an artificial terminal node, and the nodes correspond to the states. The arcs correspond to state control pairs. The start node is xk, and the end node is the next state corresponding to uk. So at x0, we have various controls that takes us to other states, x1. And from x1, we have other states, the controls that take us to x2, and so on. And for every one of these transitions, there is a cost, gk. So the system trajectories correspond to paths. Each trajectory corresponds to a path that starts at x0 and ends also at this artificial terminant node, which signifies that we have stopped, okay? Remember this figure that we had earlier with a goal state, a termination state. And each one of these arcs has a cost associated with it. So a trajectory is associated with a path. Each arc of the path has a cost associated with it. So our problem is to find the path of minimum cost, minimum sum of arc costs. But that's precisely a shortest path problem, starting from an initial state and going to the termination state. So that's an important conceptual idea, that deterministic optimal control problems with finite states and finite number of controls are in one-to-one correspondence with shortest path problems. The reverse is also true. If you have a shortest path problem, you can pose it as an optimal control problem. Okay, so let me give you an example of this idea representing the problem in terms of a graph. This is a classical combinatorial problem, the n queens problem, involving an n by n chessboard, and you want to place n queens on the board so that no queen attacks any other queen using the normal moves of chess. So an example, this example is a 4 queens problem. An example of a solution of this problem is this one. The 4 queens have been placed in squares so that no 2 of them are on a straight column on the row, the same column on the row, and no 2 of them are on a diagonal, same diagonal. Okay, so how can we pose this as a dynamic programming problem? We consider as states various board positions involving no queen, at this stage, just 1 queen, 2 queens, 3 queens, and finally 4 queens. And we introduce transitions corresponding to placements of queens. So let's look at this initial empty position. We have the various possibilities. Place a queen in this leftmost square in the first row. Place the queen on the second position. We can also consider place the queen in the third position, but this is the same as this one. It's just symmetric. And also at the place of the rightmost position in the row, but this is symmetric to this one. So we are going to omit those because they lead to the same computations. Okay, so that's stage 1. From empty board, we place 1 queen and get to one of these 2 positions. And then from each one of those, we place 1 more queen. So from here, we can place 1 here, which is feasible because the second one does not attack the first. Or we can place it here. Again, they are not in the same row, column, or diagonal. So the possibilities are infeasible, and therefore we don't consider them. Then from here, we get these 2. From here, there's only 1 possibility for placing a queen in the second row, which is this one. If we place it here, here, or here, they attack each other, so that's not feasible. So from each one of those states at stage 2, we consider the successor states. Now from here, we cannot place any queen in any one of those positions in the third row without having them attack each other. So this one is a dead-end position. And a dead-end position takes us to the artificial termination state with cost 1, okay? Cost 1 means that we have failed we have we are at a dead-end position, we have reached a dead-end position. From here, there's only 1 possibility. However, from this possibility, again, we have it's not possible to place a 4th queen. It's a dead-end position, and again, it has a cost of 1. Now, suppose that we're in this position. There's 1 possibility to place a queen at this square, and then from there to place a queen in this square, and then to place a queen in this square, which is a solution. And this has cost 0. All of the transitions have cost 0, except if by force you have to reach except if you reach a dead-end position, and then by force you have to move to the termination state with cost 1. Okay, this is pretty evident what I'm doing here, but notice the correspondences. States at the initial states at the first stage, second stage, and so on, costs associated with that, transitions corresponding to different choices, and it's exactly the same in the pattern of the same shortest path problem that I had in the previous slide. Okay, this problem is quite trivial, but even an 8-queen, the 8 queens problem, which corresponds to the normal chessboard, has like 16 million possibilities. So brute force is not possible. If you go to larger boards, it's an astronomical number of positions. However, it has been shown mathematically that this problem has a feasible solution. It is possible to place n queens on an n by n board as long as n is 4 or larger, okay? And I'm not sure though if there's an algorithm that will do that. There probably should be an algorithm, but I don't know if it's possible to use an algorithm that will give a solution within reasonable time. It's a lot of computation to place n queens into an n by n board if n is large. Rollout is very simple to do. However, there's no guarantee that it will find you a solution in the end. Very frequently, it does find a solution. Anyway, some of you may want to try this problem with rollout or by some other suboptimal technique. Okay, the general structure of deterministic rollout with some base heuristic. We have seen this before. Basically, we generate a sequence of states, and at the current state xk, we look at all possible controls that lead to all the possible next states, and then we run the base heuristic from each one, and we calculate the cost of the first transition plus the cost of the heuristic from the next state. This is the Q factor associated to the pair xk and uk. There are all these Q factors that we calculate using the base heuristic, and we choose the control that has the minimal Q factor. That's the algorithm. We've been through this before. We move to the next state, xk plus 1, and continue. There are also multi-step look-ahead versions that we have discussed, although I don't think we have given a homework on it. And there's an important question here. Is rollout cost improving? Does the rollout algorithm perform better than the base heuristic that you started? That's an important question. It's not automatic that rollout is improving. On the other hand, we're going to give now conditions under which it does have this cost improvement property. But first, let's give a couple of examples. This is a classical problem, multi-vehicle routing problem, or multi-robot routing, multi-robot repair. You may think of this as delivery trucks, or you may think of it as robots, or you may think of them as fire crews trying to extinguish fires within an area that is modeled by this graph. And these vehicles, these trucks, can move one step at a time in each time period. So starting from this position here, there are 4 possibilities. This vehicle moves here, and this vehicle moves here. This vehicle moves here, and this vehicle moves here. It's a second possibility. This one moves here, and this one moves here. The third possibility, this one moves here, and this one moves here. It's 4 possibilities. And the base heuristic is to select a move for each truck that takes it one step along the closest task to do. Oh, by the way, I forgot to say that here there are some tasks that are waiting to be done, and they are valuable, and we need to do them. And the problem is to perform these tasks by the trucks going into the location of the task and performing them, and do this in minimum time. That's the problem. get the trucks to go to, at least one of them, go to these tasks in a minimum number of steps. And the motion is as I described, and the feasible solutions are all the combinations of moves by the two trucks. And the base heuristic is to look at the closest remaining task to do and move one step in that direction for each one of the vehicles. So how does the base heuristic work for this particular problem? Well, we have these tasks here, and we have the two vehicles here. Well, this vehicle finds the closest task, which is this one. And according to the base heuristic, will move here. This vehicle will look at the two tasks, and the closest task is this one, and will move here. So the base heuristic at the first step moves this one here and this one here. Then at the next move, again, they look at the two tasks. For both of them, this is the closest task, so they both move over here, perform the task, and then both of them move here, both of them move here, and both of them move here. And how many steps does this take? It takes 1 for both of them to get here, 2, 3, 4, 5. So the base heuristic requires 5 time steps to do the job. Now let's look at rollout. We consider all possible pairs all possible moves, and then run the base heuristic from each pair. So we consider this, and we run the base heuristic, which takes a long time, because yes, they pick up this task, but they have to go around to pick up this task. Let's look at another move, the move that takes this vehicle over here and this vehicle over here. Then the base heuristic tells them to go this way and this way. And the Q factor is 3 moves. So this combined motion is preferable than this combined motion according to the Q factor criterion. And at the first step of the rollout algorithm, vehicle 2 moves here, vehicle 1 moves here. At the next step, this one moves here, this one moves here. And at the next step, this one moves here, and this one moves here, but it doesn't matter. And it takes 3 steps, 3 time steps to do the job. And notice the reason for this is that the rollout algorithm has some vision, and it can tell that if both of them move over here, then it's going to be effort wasted. And they should, and if we are able to look further into the future, they could see that it would take a long time to get back to the second task, and would also be a good idea to diversify the effort. Send one track towards one task and send another track to the other track to a different task. So that's the kind of intelligence that rollout has. Not only it looks blindly one move ahead, but it looks into the future also by using the base heuristic. Are there any questions on this example?
The rollout, it requires a very good base heuristic. We can't use any random policy to explore.
If it's random, then that may not work very well. But it's a remarkable fact about rollout algorithms that the quality of the base heuristic is not crucial. It shouldn't be entirely stupid, and it should also satisfy certain criteria that I'm going to talk about later on in the lecture. But even a relatively bad base heuristic by itself can produce a very good rollout algorithm. It can, not that it will.
So like after performing rollout, can we update the base policy, like what we get the rollout policy in the previous time? So like the policy improvement.
Yes, you certainly can. But how are you going to model the cost function of the rollout algorithm? that requires a neural network, perhaps.
But like we have the system that dynamic, so when we interact with that rollout policy, can we get like the value like after interaction, can we get the estimate for the cost?
Using some kind of machine learning, in general, using some kind of a machine learning algorithm.
To get a multiple
The problem is that the computation by Monte Carlo quickly multiplies, quickly explodes with each stage of rollout. So we're going to talk about double rollout, but it's a lot more computationally expensive than single rollout. And triple rollout is very, very complicated, and so on. Okay. So doing multiple policy iterations, multiple rounds of rollout is not very practical. It's only in special situations that it might work. There's another clever trick, however, which we're going to talk about later, that you can use multiple heuristics. Instead of using one single heuristic, you can simultaneously run multiple heuristics from the same position, from the same state, and then choose the Q factor that's the smallest. That will do better than all the base heuristics. That's the cost improvement property.
That be like point-wise minimization.
Yes, if you use two base heuristics simultaneously and run them both from each state, then and taking the lowest number from the best performance of the two, then that is a super heuristic that performs better than each of the individual heuristics. That's something that you can prove. Okay, let's do another example. Search for a breakthrough path in a tree. Here we have a binary tree, and we want to get from the root of the tree to one of the leaves using a path of unblocked arcs. Some of these arcs here are free, and some are blocked. And we want to find a path like this one, consisting of free arcs. These problems arise often in searches through mazes and so on. You can make that association. And we're going to use a greedy heuristic here. We are at a certain node, and if only one of the two arcs is free, then use it. If both arcs are free, use the right arc. So at this point, the base heuristic sees both arcs as being free and uses the right arc. At this node, there's only one arc that's being free. Then it uses that arc. At this node, there's no arc that's free, and the greedy heuristic just stops there and declares that it can't find a solution. Now we can solve this problem by dynamic programming, going backwards from the leaves towards the root. And the complexity of this is quite substantial, right? It's n times 2 to the n. There are 2 to the n nodes at the leaves, and we have to take n steps down. So the complexity is 2 to the n, and grows exponentially with n. Now, the greedy algorithm has much better complexity because it looks at only two arcs at each step and goes down at most n steps. The complexity is O to the n. Now, the rollout algorithm that uses the greedy as a base heuristic has to do more computation, has to run the greedy from every node down the path. So there's a factor of n that's added to the complexity here. It's still polynomial, though. Now, it's pretty easy to see that if the greedy heuristic finds a breakthrough, the same thing is true for rollout. Rollout will just maintain that greedy path, and this is an instance of cost improvement. There's another, so that's cost improvement, but there's also another type of cost improvement here, which is in your textbook. The discussion is in your textbook, but we're not going to discuss it here. let's take an ensemble of problems where arcs are blocked or free with given probabilities. Then the rollout algorithm will be successful for some of those. It will not be successful for others. It has a probability of succeeding within this ensemble of problems. On the other hand, the same is true for the Bayes heuristic. It also has a probability, but the probability of success of the rollout algorithm is O to the n higher than the probability of the Bayes heuristic. Okay, so not only it finds a breakthrough whenever this is possible by the Bayes heuristic, but also it finds when it finds it for other problems where the Bayes heuristic does not succeed, it finds with a much higher probability, O to the n higher. These are typical performance numbers for rollout algorithms in discrete optimization problems. The rollout algorithm has a small amplification factor of complexity over the Bayes heuristic, but it also has a much better probability of success, or in this particular of performance or probability of success. And that's the trade-off that rollout typically poses: more effort for better performance. So that's what I'm saying here. Rollout improves the performance of the Bayes heuristic substantially at the expense of a polynomial amount of extra computation. Okay, so now let's focus on the cost improvement property of rollout. If you have a Bayes heuristic and you roll it out, you're not going to get necessarily cost improvement. It's not automatic. Some special conditions must hold. And there are two such conditions that we're going to discuss. One is sequential consistency, and the other is sequential improvement. And let me describe what this means. We say that the Bayes heuristic is sequentially consistent if at a given state it chooses a control that depends only on that state and not on how it got to that state. In other words, this Bayes heuristic just looks at the state where it currently are, and then it will apply the same control no matter how it came to that state. And mathematically, if the heuristic generates this sequence from state xk, generates a trajectory up to xn, then starting from the next state, xk plus 1, it will generate the same tail subsequence. So it doesn't change its mind after it gets to xk plus 1 and generates a different sequence. That's what we mean sequentially consistent. The traveling salesman problem, the nearest neighbor heuristic, is sequentially consistent. If it reaches some state, it doesn't look at how it came there. It looks forward to the nearest neighbor all the way to the end. And generally speaking, a Bayes heuristic is sequentially consistent if and only if it can be implemented with a legitimate dynamic programming policy. Remember, each one of these news look at just xk. New k looks at xk, not at previous values of the state. Greedy heuristics, like the nearest neighbor heuristic, or the heuristic we gave for the multi-vehicle routing problem, they are sequentially consistent by their nature. And however, and it's true that if the heuristic is sequentially consistent, then the rollout algorithm has a cost improvement property. On the other hand, it's also possible to have the cost improvement property under a less restrictive condition, which we call sequential improvement. And let me explain what that is. Okay, let's look at the rollout algorithm. It starts from x0, and let's say generates this red path here to state xk. And at this point, it will have found the Q factor corresponding to the Bayes heuristic, right? it will have the cost of this base heuristic. And on the other hand, when it executes the rollout search, it may find another control that's different than the one suggested by the base heuristic. And then from there, it will follow the base heuristic. So there's another trajectory here that involves this first step and the base heuristic trajectory from xk plus 1. Now, the sequential improvement condition says that this trajectory should have lower cost than this trajectory. Okay, that's what I'm saying here. The best heuristic Q factor, this one here, is less than the heuristic cost of going through here. Okay, this is the Q factor corresponding to the minimal Q factor, the best Q factor using the heuristic. One stage cost plus the heuristic cost. This is less than what the base heuristic will do starting from xk. Okay. Now, under this condition, it is possible to show that the rollout algorithm has a cost improvement property, and the proof is relatively simple. Okay. Upon reaching xk, we have obtained a current trajectory, which is the best trajectory that we have seen so far, corresponding to the rollout algorithm, and all up to this point, plus the trajectory of the base heuristic. And we will call this trajectory RK. Now, with the next rollout step, we compare this together with other ones, together with this best Q factor, and this comes out to be better than this one. So if you look at these trajectories, successive trajectories, we have, and if this condition is satisfied, then each one of these trajectories is no worse than the preceding one. So the current trajectory cannot get worse, and since R0 is the trajectory corresponding to the base heuristic starting from x0, we have that every one of we have that the cost of the final trajectory that we get by rollout is less than R sub 0. So there's a sequence of trajectories improving, and the last one is the rollout trajectory. The initial one is the base heuristic trajectory, and therefore you get this cost improvement property. Now, it's possible to show that a sequentially consistent base heuristic is also sequentially improving. Why is that? If you have a sequentially consistent heuristic, then there's equality holding here for the control corresponding to the heuristic control, because the base heuristic is a policy, satisfies the dynamic programming condition, which means that its Q factor is equal in the left-hand side, is equal to Q factor on the right-hand side. If you look at the best Q factor overall, then you're going to get something better. So that's the reason why this inequality holds under sequential consistency. On the other hand, there are important special cases where you have sequential improvement, but you don't have sequential consistency. And it turns out that there's a very important special case, namely the MPC context, model predictive control. And there you can find examples where sequential consistently holds, but not sequential improvement. And sequential consistency guarantees the cost improvement property. So this, in 2 slides, is basically the theory corresponding to rollout for deterministic problems. It doesn't always guarantee cost improvement, but under relatively mild conditions, in fact, conditions that you can enforce with a clever modification, you have that the cost of the rollout policy is less than the cost of the base heuristic. Any questions here? Okay, so what we're going to do now is have an animation involving the traveling salesman problem. And Yucha will take over and describe this animation.
Okay. Let us now look at the traveling salesman example that you have been dealing with for a while. So again, we look at this traveling salesman example where the matrix of intercity travel cost listed here, and evidently it's not symmetric, which means the distance traveling from one city to the other is not the same as the reverse traveling distance. Okay, so if we apply the nearest neighbor heuristic starting from initial city A, we first look at the distance from A to all the other three cities, B, C, D, and their values are 5, 1, and 20, which is listed in the first row here. The base heuristic, which is the nearest neighbor base heuristic, can tell us we should choose this distance and move to city C, right? And then starting from this partial tour AC, we look at the two alternatives, B or D, and we have this one chosen according to nearest neighbor heuristic and so on. And this is the complete tour selected by base heuristic, which is R0. Now, if we look at the calculation according to rollout, one step look ahead with nearest neighbor heuristic as base heuristic. So starting from the initial state A, we look at all possible next city, B, C, D, and starting from any of those partial tour, we run base heuristic. Starting from here, we run base heuristic. Two alternatives are C and D. We choose city C and continue with the subsequent construction. And similarly for this one, and we will have this as the complete tour if we choose this and so on. Now, at this point, we find out this tour, it has a complete distance which is smaller than the one computed by base heuristic R0. Therefore, we switch to this city, B, and starting from here, again, if we follow base heuristic, it's gonna follow this path, right? However, by running rollout, we're gonna look at all the subsequent alternatives, C and D, and starting from those two and run base heuristic, which is comparing the distance of those two alternatives. And as it turns out, this distance, 4 plus 3 plus 1, which is 8, is obviously smaller than this distance, which is 1 plus 1 plus 20, 22. Therefore, again, we switch to this path. And this is the end product produced by rollout. Now let's repeat the whole procedure. Starting from this city, the base heuristic gonna give us R0, which is this trajectory, 1 plus 3 plus 4 plus 20, which is 28. However, the first step of rollout give us this city, this tour, which is 5 plus 1 plus 1 plus 20, which is 27, smaller than 28. And after we get to this city, we run rollout again and switch to a different tour with complete distance, distance 5 plus 4 plus 3 plus 1, which is 13. So again, smaller than 27. Therefore, we verified this sequential improvement result. And just let me finish. And in fact, as you can see here, if we're starting from here, the base heuristic, which is the nearest neighbor heuristic, produce this path, which is the same as base heuristic starting from here and going through here. So it's sequentially consistent. Yes, please.
Case of RT, we have a lesser cost amount. So if I increase it to complete level, can I just say that I'm kind of doing something similar to DP if I increase the amount of payloads I have?
Well, if you go all the way till the end, you don't get the computational saving, don't you, right? So the whole point of rollout is to substantially reduce the computational saving to start with. And secondly, it's not exactly, if you starting from here and look all the way till the end, it's not exactly the dynamic programming we talked about, right? The dynamic programming we talked about is starting backward and going forward. And in fact, in literature, there is an alternative of dynamic programming for deterministic shortest path type of problem. You can start forward and it's forward dynamic programming, and you can look at the literature. But if you look all the way till the end, no, it's not rollout. Okay. Yes.
Can you give an example of a policy which might be sequentially improving, like which doesn't follow this linear?
Okay, we're gonna get to that in the second half of the lecture. Okay. Now let's look at a different shortest path problem, and in this case, it's symmetric, by which I mean between two cities going from one city to the other, and the reverse direction have the same distance. So this is randomly generated in a 10 by 10 grid, 10 by 10 square. And starting from city 0, we want to find the shortest complete tour that goes back to city 0. You can, of course, do dynamic programming, but as you may experience or expect, that the computation is kind of daunting. Or alternatively, you can use nearest neighbor heuristic, which is what I'm gonna show right now. So starting from city 0, it first lists all the distance starting from city 0, and look at all the distance from city 0 and choose one which is nearest. And as it turns out, it's city 10. You can visually measure it. It seems obvious. And the second city to choose is, again, compare the distance between all the remaining cities to the city 10, and you can see city 2 is nearest. So at each point, evaluate all the possible next cities that has not been visited, and the number marked here is the immediate distance from the city to the candidate city. So we can let the simulation run here, and here is a yeah. So we'll continue, and you will find out there are some patterns sort of typical for shortest path, for nearest neighbor. This kind of greedy heuristic is that it only focuses on the immediate cost and does not have this far into the future insight about the problem. As it turned out, in the initial phase, it seems quite promising, but when it's approaching to the second half of the phase of the problem, the remaining cities are all the ones that is far away, and typically you will see there's this kind of crossing passes happening in the second half of the tour, because it's kind of short-sighted to ignore the potential detour is going to occur. For example, starting at here, it's short-sighted, blindsided by this nearest neighbor and didn't recognize it may be better to steer to this direction. Okay, so this is the nearest neighbor heuristic. Now let's look at rollout. So for the same problem, starting from starting from the initial city. Now, the number listed here is not anymore the immediate distance from this city to that city, but rather is the corresponding Q factor, by which I mean this number will be is the number that adding the distance from city 0 to this city plus the complete tour starting from this city goes through all the remaining ones by following the nearest neighbor heuristic and go back to 0. So the numbers here listed here are Q factors, are not immediate distance between those two cities. So by using Q factor, it encodes, have this long vision into the future of what is the potentials of visiting this city. And here is the interesting point. If you look at here at city 8, the nearest top 3 cities, according to nearest neighbor heuristics, are this city, and this one. And the city 12 is 4th closest. It's not the top 3 closest city. But according to nearest neighbor heuristic, this one has the lowest Q factor. Therefore, despite being the 4th closest city, rollout chooses that city to visit next. And we can continue with the simulation. And as you can see, at each point, it evaluate all the candidate next cities, feasible next cities, and choose one with the smallest Q factor. Another interesting thing is starting from the beginning in the traveling salesman example, starting from beginning, you need to visit all the subsequent feasible cities, which is all the remaining ones. And then when approaching the end of the tour, the remaining cities are fewer and fewer. So starting typically the amount of calculation required in the initial phase of rollout and the end phase of rollout is different. We will see later on there are candidates that variant of rollout that kind of deal with the initial phase computational challenges. Okay, so at this point, the tour is complete. And as you can see, because of this long vision encoded by rollout, by looking into the future, running the base heuristic, we do not have this kind of crossing passes that lead to detours in the end. Any questions here? Okay, so let's have 15 minutes break and continue with the second half of the lecture. All right, let's get started with second half of the lecture. As discussed in the first half of the lecture that we have discussed in detail, rollout applied to deterministic problem, and some of you have raised the question about potential problems of rollout. To start with, how the quality of base heuristic can affect the rollout policy. And the second is we have not promised that rollout going to produce optimal policy. What we can say is that under certain condition, that rollout policy is going to perform better than the base heuristic. But what if those conditions does not hold? And also, even though compared with base heuristic, there is a small amplification factor in terms of a computation involved in rollout, which should be substantially less than dynamic programming. But what if this amplification is still way too large? What are we gonna do if the computation is still daunting for the task at hand? And now we're gonna attack some of those questions. To start with, let's look at the problem of too much computation involved in rollout. So what if you still don't have enough computational budget, either computational time or resource to conduct exact rollout? at every stage. And what we're going to do is we introduce this simplified rollout algorithm, assuming that the base heuristic satisfies sequential improvement condition. Recall that in the rollout, at a typical state, we compute all the Q factors or corresponding to all feasible states and look for the one which have the smallest Q factor. And because of sequential improvement condition, this Q factor is definitely, the smallest is definitely less than the one given by the base heuristic. Now, the simplified rollout tells us, instead of looking for the one that attains the minimum of the Q factor, we can choose as the rollout control any control that is smaller than or no more than the smaller than the one given by the base heuristic. So hk of xk is the cost of trajectory generated by the heuristic from xk. As a result, we can focus on a small subset of promising controls. Suppose that at xk we have 10,000 controls to deal with. We may only look at 50 of them, which are the most promising ones according to some pre-computation, and only enumerating among the 50 promising ones. Now, remember that in the linear quadratic problem we discussed earlier, this minimization computing with respect to Q factor can be done exactly according to some analytical formula, right? But in the case where the control is discrete, how you're going to deal with, how you're going to solve this rollout minimization? Typically, what you do is you construct a for loop and enumerating all the feasible controls, and then find the one that attain the minimum of the Q factor, right? Now, to achieve implement this simplified rollout, I suggest two ways that can be done. The first is you still do this for loop, enumerating possible controls. But in addition to comparing with current best, you also compare with the cost produced by the base heuristic. As soon as you find out a control that give a Q factor smaller than base heuristic, you can break from the for loop and move on to the next stage, right? So this is one way to find out a control, any control that satisfies this inequality. Alternatively, what we can do is by performing some pre-calculation according to some heuristic, construct a subset of all the feasible controls and do for loop among those feasible controls. So those two alternatives can both achieve the same goal, but they have their pros and cons, and you can try out those ideas in some of the subsequent homeworks or in the traveling salesman examples we have touched upon. And to give you an example, in the Wordle application that we covered in earlier lecture, and we will go again, revisit that example. At the initial phase, the control set consists of 12,500 around control options you choose from. But instead, in the actual application, according to some base heuristic, a subset of promising next word is selected, and this subset consists of only 20 to 50 states, 20 to 50 words. So it's a substantial reduction of the candidate control you choose from. Now the question is, by doing this, do I still maintain the performance improvement, cost improvement property? And the answer is yes. Suppose that we have the base heuristic has the sequential improvement property, then the rollout under the rollout policy obtained under from the simplified algorithm still has this property that its cost is bounded by the cost given by the base heuristic. And the reason actually is quite simple, straightforward. You can again construct this sequence of tentative trajectories or 0 or 1 or 2 until Rn. And given that the control you select satisfy this inequality, this line of proof still goes through. Any questions? Okay, let's go back to this traveling salesman example and give you an idea how the simplified rollout can be applied. Recall that I mentioned earlier that in the initial phase, starting from city 0, the exact rollout need to look at all the possible next state, next city, which is 14, and starting from any of the 14 states and run base heuristic, which is the nearest neighbor heuristic, and compare their Q factor and so on. Now, in this simplified rollout variant, instead of looking at all possible next city, which has not yet been visited, I only look at the top 3 nearest city to the current end of the partial tour and evaluate their Q factor. My rationale is that those nearest city should be good candidate. So it's basically something you decide how to construct this subset of control that you select. So starting from this, the initial city, you look at the nearest neighbor, 3 nearest city, and evaluate their Q factor by running nearest neighbor heuristic, starting from those top 3 city, and choose the one with the smallest heuristic, the smallest Q factor. And in this case, the choice is identical to the rollout algorithm. Now we move on to this stage and look at top 3 city, which is the nearest to the city 8, and run the base heuristic and find out this one, the city 10, has the smallest Q factor. Actually, at this point, you may recall that the rollout, in fact, chose city 12. The city 12, despite being the 4th closest city, has the smallest overall Q factor. However, given that according to the rule that we have set, which is only look at the top 3 nearest city and evaluate their Q factor, we basically prune this city in the city selected by rollout. So we continue this procedure, and at every step, we look at the top 3 and run the base heuristic and move on and so on. And let me fast forward a little bit. So yeah, it select complete the tour in the end. One common character you see the path constructed by the simplified rollout is that it also does not contain this cross passing. So it still maintain this looking to the future character of rollout. And it reduced the computational burden substantially, especially in the initial phase compared with computing 14 Q factor, you only compute 3 Q factors, which is 1/5 of the computational effort. But of course, nothing comes free. And in this case, you get a complete tour, which is slightly larger than the exact rollout. But the good thing is at every stage, you compute, you know exactly the number of Q factors you're going to evaluate. It's not varying dramatically. So this is one way of conducting simplified rollout. Basically have this 2-phase process. The first phase is to construct a promising subset of control, and then evaluate running for loop, evaluate all the controls within the subset. Now, a question here is, what I have done is choose the top 3 nearest city and evaluate their Q factor. Does this construction satisfy what I described earlier, which is this inequality? Anyone has some idea?
Yes, it does. Why should you're always looking at nearest neighbors anyway?
Okay, let me give the answer. Sorry. Well, actually it does. So, so the reason is, remember that we want to find a control that at least perform no worse than the nearest neighbor heuristic, right? That's the whole point of this equation. We want to find a control, any control that has the corresponding Q factor, which is no more than the one produced by the base heuristic. Well, base heuristic to start with is a policy. It's sequentially consistent, which is nice, which means starting from here, if we follow the base heuristic, which is the nearest neighbor heuristic, it's going to construct some paths. And then starting from here, the tail portion of the path is the same. So when we construct the subset of control, we already, inside this control subset, we already include the control selected by base heuristic. So we are always compare against the cost selected by the base heuristic. And if we choose something that is better, we already beat the base heuristic. So if you look at it here, at this point, this is the nearest neighbor, right? And this Q factor is the entire complete tour generated by the base heuristic. So at this point, we already compare against the base heuristic. And if we find something better, then we choose that. And if we don't, we stick to the base heuristic. So by doing so, we always ensure that inequality always hold by when we look at this subset. So this is one, generically, this is one way to deal with constructing that subset, which is using the same policy that use as base policy to construct the subset for simplified rollout. In later lecture, we're gonna talk about another more systematic approach, which is multi-agent rollout. So it's a different way of constructing this subset. Okay, let's move on to the next base heuristic, next variation. In the first variation, our primary goal is to reduce the computational effort or computational burden, right? We want to reduce the number of Q factor we calculate and compare. And in the second case, suppose that instead of restrictive computational burden, we have plenty of computational time or resource available. But rather the problem is we don't really have a good heuristic that works for all states. Suppose we have a heuristic that works for some state, and we have another heuristic that works for some other states. And how can we combine the strengths of those heuristics? As the professor mentioned earlier in the first half of the lecture, there are simple ways to combine them together. The idea is to construct a super heuristic, which runs all the heuristic at each state encountered and selects the best out of the trajectories produced. And this super heuristic can be viewed as the base heuristic for a rollout algorithm. And as we will verify shortly, if all heuristics are sequentially improving, then the same is true for this super heuristic. The proof is straightforward. First of all, we write out explicitly the sequential improvement condition for each of the M heuristics. So the sequential improvement condition says for every state, at every stage, its Q factor, minimum Q factor should be no more than the heuristic cost starting from xk, right? So, and this should hold for each and every heuristic. Now we take one additional minimization over both sides of the inequality over M. And this inequality should still hold, right? And we are allowed to exchange the order of the minimization over control and the minimization over the heuristic. Then we reach this inequality. And what this inside expression says is that at state xk, for every control uk, we run all base heuristic and find out the one which is the smallest of the M heuristic, and that Q factor would be the Q factor represent the cost for UK. So for every UK, we run M heuristics and minimizing over those Q factors. And that is the Q factor of the super heuristic. And since this inequality holds, minimizing over M on both sides also holds, and exchange order of minimization, we reach this inequality, which is sequential improvement condition for the super heuristic, right? Of course, again, nothing comes free here, and the price we pay is instead of running for one Q factor for each UK, now we need to run M Q factors. So there's the amplification factor M for the rollout with super heuristic. Again, the challenge, you need to remember which, if you want to apply variance of rollout, you need to remember what is the primary challenge you are facing. Are you facing the challenge that you are running short of a computation budget, in which case it's not a good idea to run super heuristic, right? It only makes matters worse. But if the problem is you do not really get adequate performance due to the bad base heuristic, then simplified rollout will not save you. You should think about things like super heuristic, right? Let's get a little bit deeper into what could happen if the cost improvement property fails. And this especially happens without the sequential improvement condition, then we will not have the cost improvement property. We look at this very simple example, starting from x0, and suppose that our base heuristic is such that starting from x0, it produces a sequence of control and state u1 star, x1 star, u0 star, x1 star, u1 star, and x2 star, which happen to be optimal. In part due to this transition has a very high cost. So nothing stops us from making such assumptions. And assume instead of being sequentially consistent, it's not sequentially consistent in the sense that even though starting from x0, it produced this path, the base heuristic produced this path, when starting from here, the base heuristic select u1 bar rather than u1 star. Again, nothing stops us from doing so. And then at x0, if we apply rollout, we look at the both candidate choice u1 star and u1 tilde and evaluate the Q factor of corresponds to this control and this control. For this control, the Q factor going to correspond to this path, which is larger than the cost of this path. As a result, the rollout gonna select U0 tilde rather than U0 star as the first control. So this is what it says here. The Q factor for U0 star, because of this high cost, is larger than the Q factor of U0 tilde. So the rollout is going to select U0 tilde and moves to the non-optimal next state X1 tilde. Therefore, in absence of sequential improvement, the rollout can deviate from an already available good current trajectory. Again, if we look at here, why there is no sequential improvement? Because at this point, the Q factor it considered is corresponds to this path and this path, and neither of those two is better than the cost starting generated by base heuristic starting from X0, basically this optimal path. Therefore, it does not have sequential improvement condition, and the produced trajectory can be inferior to the trajectory generated by the base heuristic. However, this suggests a possible remedy. So instead of blindly follow base heuristic, which may not be sequentially improving, we can keep track of what is the current tentative best trajectory and stick to this best trajectory if rollout does not give us something better, right? And that brings us to fortified rollout, which restore cost improvement for base heuristic that are not sequentially improving. So at each step, it follows the best trajectory computed thus far, which means given that, suppose that starting from X0, after some control selection, we get to the current state Xk, and this portion, we call it permanent trajectory. But in addition to this, we also keep track of what has been a tentative best trajectory denoted by TK bar. And that's some trajectory we have stored thus far. So in addition to the permanent rollout trajectory, we also store a tentative best trajectory. And this is the best end-to-end trajectory computed up to stage K. Now, what happened is that in addition, in the rollout, at this point, we're gonna evaluate all the possible feasible control, and starting from all corresponding next state, we run rollout, we run base heuristic, and we compute the corresponding Q factors. Given that the base heuristic is not sequentially improving, it's always not sequentially consistent, which means starting from this one, it can deviate from the tentative tail portion of the best trajectory. And let's say after comparing the Q factors, and we find out according to rollout, this is the minimum Q factor computed according to the standard rollout. Then in addition to that, we also compare the cost of this trajectory with the tentative best trajectory. If this trajectory has a cost which is inferior to the tentative best trajectory, we select the control suggested by the tentative best trajectory and move to the next stage. If, on the other hand, the minimum Q factor has a cost that is smaller than the tentative best trajectory, we switch to this control, UK tilde, and update the tentative best trajectory to be this one marked in green. Again, nothing comes free. And when applying fortified rollout, compared with standard rollout, we need to do two more things. One is we need to store the complete trajectory corresponding to each Q factor when best Q factor when compared with the tentative best trajectory. And second is we need to compare the minimum Q factor with the cost of tentative best trajectory. So there are two additional things we need to do in addition to the standard rollout calculation. But those things are kind of trivial compared with the computational requirement in general. So this is the fortified rollout. And fortified rollout is applied to deal with the case where you are not sure whether or not sequential improvement condition hold, right? So if you are not sure if the base heuristic you use satisfy the sequential improvement condition, then it's always a good idea to implement the fortified rollout variation. On the other hand, if you are sure that the base heuristic you apply satisfy the sequential improvement condition, then this is not necessary. In particular, if your base heuristic is a policy in sense of dynamic programming only rely on the current state, then it's always sequentially improving, then it's not necessary. And the reason is, if we look at here, again, in the same example, suppose that our tentative best trajectory select this one, then when we compare here, the heuristic generated starting from this one gonna be identical to the tentative best trajectory. So you don't really need to store this tentative best trajectory because it's gonna be reproduced. Okay. Now let's illustrate fortified rollout using the counterexample we just talked about. So at state x0, the fortified rollout stores as initial tentative best trajectory the unique optimal trajectory, which is this one, generated by base heuristic. And in the first rollout step, it computes the Q factor corresponds to U0 star and U0 tilde by running from x1 star and x1 tilde, respectively. And as we mentioned earlier, the rollout is going to select this one with smaller Q factor. And if using standard rollout, it's going to deviate from the optimal trajectory and goes to apply U0 tilde. However, in fortified rollout, after the computation to figure out which is the smallest Q factor, it also computes with compare against the tentative best trajectory. And in this case, it's optimal. As it turns out, this tentative best trajectory is better than the minimum Q factor. Therefore, it discards U0 tilde suggested by rollout and in favor of U0 star, which is dedicated by the tentative best trajectory. It then sets the permanent trajectory to be x0, U0 star, x1 star, and keeps the tentative best trajectory unchanged for the later portion. So this is how fortified rollout can be applied to restore the cost improvement property. Well, up until this point, we have talked about problems where we say we know the system dynamics, we enumerate all the possible controls at current stage, and we run simulation according to base heuristic, we compute the Q factors and so on. But if you think about it, what we really need is just to find out a control that corresponds to something better given by the base heuristic, right? In other words, this simulation can be run using a computer simulator. We don't necessarily need to know what is going on under the hood of this computer simulator. All we need to know is it generates some trajectory according to some base heuristic, and there are certain ways to rank those base heuristics and tell those Q factors and tell us which one of the Q factor corresponds to which control is the best among those, right? And that brings us to this model-free variant of rollout, which we call model-free rollout with an expert. And we will talk about its application to general discrete optimization problem in this form, We want to minimize over some component u0, u1 to un minus 1 of certain function g. We have touched upon these problems in its special cases, such as traveling salesman problem. But in the textbook, there is a general reformulation of this generic discrete optimization problem into a problem that can be tackled by dynamic programming. Briefly, at initial stage, we just think there is the artificial state, and we look at all the controls u0, and we apply a certain u0 and move on to the stage 1. And this stage 1 composed of control has only one control element. Composed of state contain only one component. So after k stages, the control is partial solutions, u0, u1, u2 until uk minus 1. And the dynamics is simply appending the new control component you selected at that stage and get a extended partial sequence of control. And this problem has no intermediate stage cost except the terminal stage. It has a terminal cost described by this function g. So this is the dynamic programming formulation of this discrete optimization problem. And this model-free rollout with an expert assumes that we do not need to know this function g. And we don't even need to know those control constraints set u0. We don't need to know explicitly the form of the base heuristic either. All we need to know is that there is a way, some computer simulator, that given any partial solution u0 to uk plus 1 can tell us what are all the possible feasible next control component we can consider. And starting from any of those partial solutions, it can generate all the subsequent portions that give us complete solution. So in other words, given a partial solution, u0 until uk, there is a computer software which tells us what are all the feasible uk plus 1 we can consider. So this is one software. The second software is that given all the partial solution u0, uk plus 1 tilde, it gives us starting from this partial solution, it gives us complete solutions. So starting from any of the partial solution, it provides complete solutions. So this is the second software. The third software is that given any two complete solution, it can rank those two complete solutions, basically tells us which one of those two is better. There are some subtle points here. We need to make some assumptions about those software, human or software expert. In other words, we need to require this expert has certain property that suppose we have 3 complete trajectories. Trajectory 1, 2, and 3. Let's suppose this expert says that trajectory 1 is better than trajectory 2, and trajectory 2 is better than trajectory 3. Now, this expert need to have such a property that is declare trajectory 1 is better than 3. In other words, it need to have this consistent rule that decides which one is better. Otherwise, let's say if this expert says 1 is better than 2 and 2 is better than 3 and 3 is better than 1, then there's no way for us to find out which one is the best. So there need to be a way that it can rank any two of the solution and declare which one is best. And deterministic rollout can apply to this problem at this point because we have all we need. Now, let's just imagine an example. I don't know, perhaps some of you has seen this interesting application where some people set up two state-of-the-art large language model and ask them to apply chess against each other. And neither of them perform quite good. Now, on the other hand, they can still act as an expert. And in fact, in one of the follow-up lectures, we're going to talk about a meta algorithm where we incorporate an existing chess engine and improve upon it. Now imagine we use some of those language model available, and imagine we have some base heuristic to play chess. Then one way the language model can be incorporated into this application is we try all the moves and counter moves, and we don't really know which one of them is most promising. We can give this language model all the ending positions and ask this language model to evaluate, right? Or play all the way till the end and ask the language model to evaluate which one is the best. So this is one way this expert system can be incorporated into this framework. We don't really know the inner working, why it prefers this one over the other one. All we need to know is it gives some preference and declare which one is the best. Okay, now here is a more concrete example applied to the RNA folding application. And this is an article published a few years ago where the professor collaborated with some colleagues here. And the RNA folding is an important application in the computational biology, where we are given a sequence of molecules by the name of nucleotides. And each one of the molecule, we want to match some of it with the other molecules according to certain criteria and under certain constraints. Those molecules have 4 types, A, C, G, U, whereby you can match a type A with a type U, and you can match a type C with a type G, and not the other way. So that's one constraint. The second constraint is, suppose this is a partial folding, whereby we have matched this molecule with this one. We cannot create crossings, by which I mean this molecule cannot match with this one or this one because it's going to create this crosses. So there are some constraints. And given a partial pairing, we want to make decisions in terms of these molecules and the subsequent molecules. How are we going to match those molecules with the remaining ones in order to create a structure, RNA structure, that is interesting. By interesting, the meaning of this interesting going to be a little bit clear later. So for this problem, if we frame it as a dynamic programming problem, the state is any of the partial folding. At this point is this sequence of molecule together with its folding. This one matched with this one, and this one we declare it's going to match with some other subsequent molecule. We don't know yet which one it's going to match, but we know it's going to match some of them. And at this point, this molecule, we have 3 controls. One is close, so it's going to match with this one. And the other is null, which means this one will not be matched with any molecule. And or open, which means this one going to match with some subsequent molecules as well. Now, we are given a base heuristic, which is a folding software, which is that given any partial folding, it's going to generate a complete folding using some criteria. which we have no idea. What is the exact inner working? Why do this or that? But what we know is it satisfies the constraint we specified earlier, and it can provide the complete solutions. So this is a partial folding software. In other words, starting from this partial folding, we try first close, which will match this one with this one, and create a partial folding. And then we pass this partial folding to the software, which create a complete folding. And similarly for this one, we pass it to the software and create a complete folding and so on. So we run the partial folding software for 3 different initial partial foldings, create 3 complete foldings. And then the second ingredient is we need this expert software, which evaluate those 3 complete foldings, which one is the most interesting. Well, at this point, there is no consensus yet for among the biologists. What does it really mean by interesting or useful or most or correct or optimal? So there's not really any definition of optimal. There is no explicit cost function here. But what can be said is if we judge by the same expert, the one produced by the rollout, in this case, is this one, judged by the expert is the best, gonna be the one selected, which corresponds to this complete folding, and we move on to the next stage. As you can see, we don't really know the inner workings of this partial folding software. We don't know the inner workings of this expert software, but what we can say for sure is the one generated by rollout, judged by this expert software, is better than the one generated by this partial folding software. Okay. Now that concludes this lecture. For the next lecture, we're going to talk about rollout with multi-step look ahead. We're going to talk about rollout applied to constraint problems, and in particular, its application in integer programming problem. You will have a new homework due in 2 weeks, which is a computational exercise, applies spiders and flies, and using rollout and multi-agent rollout. And so there are 2 parts, computational exercise you will work on, and multi-agent rollout. We have not yet get into details, but you can work on the first half. About your project, you should read the guideline for the term paper, which has been posted on Canvas. Feel free to send us email for clarification and questions. And please send us by the end of the spring break, 1 page or less proposal about your term paper, either be it read and report or a mini research project. Thank you for your time.